here we give you another example showing the semantic concept detection. This paper was published in year 2005 in ACM Multimedia System Journal, and this work was done by the researchers in National Taiwan University when I was a PhD student. So the general idea is, right now we know that the most important problem is the semantic gap between features and the semantic concept. So the idea is based on the audio, based on the visual content or audio content. In this work, we focus on action movie. Based on action movie, we can extract many features like ZCR, energy, bandwidth, MFCC. And the target is we want to detect gunplay or car chasing scene. This would be very high-level concept, and we cannot directly build a model to detect gunplay and car chasing based on low-level features. Therefore, we refer to some filmmaking rules and a convention to define the mid-level representation that include several audio effects like gunshot, explosion, engine, and car braking sound effect. And how can we detect such sound effect? We can use the knowledge about audio effects. As we mentioned before, we have already introduced the work to detect audio sound effect based on low-level audio features. Therefore, we can develop the sound effect recognition models to detect audio effect. And then based on the score or the likelihood of these audio effects, and by modeling the distribution of such audio effects, we can detect high-level concept. And this is the whole framework. So given audio frame, the whole framework is divided into two parts. The first part is the audio effect modeling. The second part is the semantic concept modeling. So given the audio string, we extract feature first, and then we construct several hidden markup model, and each of which describe a specific audio effects. And then we can estimate the likelihood value of each audio effect, and then we construct the specific and word distribution and estimate the confidence. And based on the confidence score, we construct the mid-level representation. And based on such mid-level representation, we construct probability model that would be generative model or discriminative model to detect semantic concept labels. So the whole ideas are quite similar to what we have introduced before. But we focus on action movies and focus on audio concept. In the whole framework, the most important part is the confidence score. We would like to evaluate how likely an audio segment belongs to a specific audio event. So we give you this illustration before. By extracting audio features, we construct several audio effect hidden markup model like engine, gunshot, and explosion. And we have already the training data consisting of engine sound, gunshot sound, and explosion sound, and so on. So if we input the engine sound to the engine model, then we can get a lot of likelihood value, and we can construct the distribution of the likelihood value. And if we give the gunshot sound and explosion sound to the engine model, then we can construct the world distribution of engine event. That means if we intentionally input the non-engine sound to engine model, the likelihood score will distribute like this. And how likely a given audio sound belongs to engine sound effect can be measured by such confidence score. That is input to the engine sound effect model. Then we can get we can get a likelihood value x. And for such x, how likely it belongs to engine sound is the numerator, and how likely it belongs to not engine, the denominator is this. And both these two values are likelihood value, and this is called the likelihood ratio. Okay, so based on the likelihood ratio, we can measure how likely an audio segment belongs to a specific audio event. And remember that because we focus on gunplay and a car chasing scene, so it's not enough for us to just focus on 1 second audio segment. Therefore, we aggregate several analysis windows into textual windows. So this idea is from the audio content analysis. Okay, so we will consider every 5-second audio segment, and we will calculate the means of confidence score to construct the mid-level representation. And given this mid-level representation to higher level modeling, we can detect higher level audio concept. For the higher level concept modeling, we also try generative modeling and discriminative modeling. For the generative modeling, we use hidden Markov model because it's preferable to model time, duration, density, because confidence score don't remain the same at every time instant. For supported vector machine, we exploit SVM classifier to discriminate the texture of gunplay and car chasing scenes. Therefore, we can imagine that when we use the hidden Markov model, so given audio stream coming from an action movie, then we will extract audio confidence score for each audio segment. Okay, and for each segment, basically these segments are overlapped in 50%. This audio segment, we can extract audio confidence score 01, 02, 03 is to 04, OT. Then we can model this this time series of data by hidden Markov model. But when we use SVM, we just we also segment it into many audio segments. However, we classify each audio segment into gunplay or car chasing or others. We classify each audio segment, okay, rather than we jointly consider the whole time series of data. For the generative modeling, we evaluate the likelihood, so we construct the hidden Markov model lambda s, and we estimate the probability of such observation sequence generated by such hidden Markov model. And if the probability is larger than a predefined threshold delta, then we say that this audio segment has some audio scene or audio concept. Okay. And for the discriminative model, we will classify the pseudo-semantic feature. The so-called pseudo-semantic feature is the same as the mid-level representation we said before. That is the aggregation of confidence score. Okay, we classify the pseudo-semantic features into gunplay, car chasing, or others with a multi-class SVM. And this is a performance. To evaluate individual audio event, we evaluate gunshot, explosion, car braking, engine. Okay, and these are the precision and the recall value. And generally, we can achieve more than 80% precision and 70% recall. For the training data, we have 100 audio clips for each audio event, and each event lasts for 3 to 10 seconds. For the test data, we use 6 clips, and each length 3 to 5 minutes. Okay, and how about the performance? we compare this performance with other work, and although it's not a fair comparison because we don't use the same evaluation data, but we can see from the numerical value, we can see that the proposed work works very well, because from the reference 29, they detect a claim, a whistle, commander speech, and a silence, and they can achieve more than 90% accuracy. For reference 14, they detect laughter, applause, and a cheer. Okay, so this paper was introduced in the online lecturing videos before. Okay, and we can see these audio events are different from ours. But at the reference 30, they also detect explosion, and the accuracy is 86.8%. And based on our approach, we also detect explosion. We achieve more than 90% accuracy. And these are the performance for semantic concept modeling. And in this data, the training data include 24 video clips, and the testing data includes 6 clips, and each clip's length is 3 to 5 minutes. So these are very realistic action movie data. And the average precision and score for gunplay and car chasing are here. The cells with number A are the performance obtained based on SVM, and the precision and recall number B are that obtained based on Hierarchical model. And we can see that more than around 70% precision and recall jointly, if we jointly consider them, around 60% precision and recall can be obtained by SVM. And if we consider Hierarchical model, the performance are similar, but with slightly worse than SVM. Here are some detailed results. For the gunplay, we show some detailed results from the following movie clips. Okay, like We Were Soldiers, 44 minutes, and Imposter, and so on. And we can see some for some video clips we have better performance, and for some video clip we have slightly worse performance. So we can see here is that such concept detection is totally content dependent. The performance of concept detection is content dependent, depending on the quality of audio and the complexity of the audio. Because if there are many sound effects mixed together, then accurately detect the semantic concept would be difficult. Okay, like the rock, you can see here for the car chasing scene, we have worse detection accuracy. We have worse precision. Okay, in detecting car chasing in the rock, because the corresponding movie clips include many music. Okay, and it's difficult to discriminate music and other related audio effect like car braking or engine sound. Okay, so car braking, engine sound, and music are mixed together, so it's a little bit difficult to accurately detect the car braking sound in such movie clip. And here are some reference mentioning the semantic concept detection. So this reference is the paper we have introduced before. That is one of the most early work to do semantic concept detection. And this is our paper. And we also recommend you to read this paper published in IEEE Translations on Pattern Analysis and Machine Intelligence, published in year 2006. And you may be also interested in the data set or the common benchmark for us to do video concept detection. That is one of the most famous data set is traffic. Then you can refer to this paper.